Hello class, these are our Algebra 2 notes. We're looking at section 11a. We're splitting it into two parts. We're looking at Introduction to Sigma Notation. So a series is when we take a sequence and we add the terms together. So when the terms of the sequence are added. A finite, that's interesting, my pen is not working, let's try it again. A finite series is when it stops, when we're adding something that stops, like 2 plus 4 plus 6 plus 8. It doesn't have the dots at the end, so I can add it up, and that's going to be 10, 10, so it's going to be 20. So an infinite series is like 2 plus 4 plus 6 plus 8, and then we write plus dot 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 to show that it goes on forever. So sometimes there's an actual sum, sometimes it approaches infinity, or it is infinity. It just grows and grows and grows. But sometimes we actually have a sum, which is interesting. We'll look at that tomorrow. So summation notation for a series. So we call it summation notation, but this is sigma. So sometimes they call it sigma notation instead. The bottom part here, this I equals 1, that is my lower limit. And that gives me my starting term. At the very top where it says n, that's going to be my upper limit. And that's going to be where I stop. So it's my end term, my last term. And then f of I is the part that I'm adding over and over again, the part that I'm substituting things into. So that's basically our rule, if we think about like an nth term rule that we've been working with. So the way I would do something like this, summation notation, I'm starting at 1, I'm going up to 4, I'm substituting all those numbers in for I. So first I would substitute 1 in for I. So I would have 2 times 1 plus 3. And then because it's summation notation, we're adding. So then I have a plus sign, and then I sub in 2. So 2 times 2 plus 3. And then I sub in 3. 2 times 3 plus 3. And then I sub in 4. 2 times 4 plus 3. And then when I get to 4, that's when it tells me to stop. So now I'm done adding them up. So it's like I took this thing, right, that expression, and then I added it again and again and again, and I plugged in progressively larger numbers. I started with 1, and then 2, and then 3, and then 4 was my last one. And now I've just got to go through and calculate all of this. So 2 times 1 plus 3 is 5, plus 7, plus 9, plus 11. And so that's going to make 16 and 16. That's going to make 32. So now we're going to work backwards, and we're going to see if we can take something that is written out as a series. So it's kind of like having a sequence, right? It's just I'm adding it over and over and over again. So I still want to think about all of my sequence rules. I still want to think about how am I adding something each time or multiplying something each time? And it turns out that we're adding 7 each time. And this is where we're starting at. It's arithmetic. So when I go to write a rule, I am going to write my sigma notation because I'm adding a bunch of stuff up. And then this is where I want to choose. Am I starting at 1 or am I starting at 0? And so I'm going to do it 2 different ways. So if I start at 1, I know that I'm going to be ending at 1, 2, 3, 4, 5. And the thing I'm adding over and over and over again is going to be like my nth term rule for an arithmetic. So it's like my explicit rule. So I start with 5 plus 7 times, and then it's going to be I minus 1 because I started with term 1. I'm going to put a big or over here. What if we started with 0? So if we started with 0, I write I equals 0, and then 0, 1, 2, 3, 4. I would be ending at term 4, and this one would be 5 plus 7 I. So hopefully this part looks familiar. This is what we've been doing, right? We've been writing this rule, but instead of writing 5 plus 7 times I minus 1, we've been writing something like f of n, right? We've been writing like f of n equals 5 plus 7 times n minus 1. We've been writing something like that instead. So it's the same kind of idea. It's just now instead of calculating a specific term, we're adding them all up. Our next example, we're going to try and write again. So I want to think one more time about just this list of numbers, 3, 6, 12, 24. So I'm starting with 3. And then what am I doing each time? Well, it looks like I am multiplying by 2. So I'm starting with 3. It's geometric. We're multiplying by 2. So again, I want to think, what is my rule for this? And maybe we start with f of n first. Like, I don't know if that's the right thing to do or not. But maybe we start with f of n. So if I used if I had a term 1, if I let this be my first term, then my f of n would be my start, 3, times my growth factor, 2, to the n minus 1 power. That would be for n greater than or equal to 1. So to change this to sigma notation, I'm starting at I equals 1. And really, I could use n there if I wanted to. It's fine. And I'm doing 1, 2, 3, 4. Actually, it says dot, dot, dot. We're going to infinity. It's going forever. And this is going to be 3 times 2 to the I minus 1 power. So if I was going to write this with the 0 term instead, 0th term. So if I'm starting with 0, maybe starting with 0 would be a better way to word that. So if we start with 0 instead, how would we do this? So let's write start with 0. So if I start with 0, then I would have I equals 0 at the bottom. This would still be going to infinity, but let's think about our nth term rule for this. Our nth term rule would be 3 times 2 to the n power for n greater than or equal to 0. So I'm writing that thing, right? But instead of an n, I'm just using an I. I could totally just make this an n at the bottom instead if I wanted to. I could keep everything in n. It's fine. It's whatever letter that you want to use. I is really common, k is really common, n is really common. So I'm just using I because we started out with I. And I want to keep our nth rule stuff different from our sigma notation stuff. But if you're more comfortable with n, use n. So this is going to be 3 times 2 to the nth power. So you do not have to do 2 answers. You just have to do 1. So I know when I'm checking this that if you have an I minus 1 here, you should have an I equals 1 here. If you have an n here, you should have an I equals 0 here. So your things should agree, right? They should match. But I don't care which way you do it. So we're going to practice this some more, writing a series with summation notation. So these are the ones that you're practicing on your own. I think for now you just practice problem 1, and then we check them over. So go ahead and pause the video. When you come back on, I'll explain it. So remember, we have a sequence here. 7, 14, 21, dot, 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 all the way up to 77. So I am trying to show adding all of these together. And so 7 is my first term. I'm going to call it my first term. So what term is this one? This one is 7 plus 7 times 10, right? That's what's going on. So I want to think about how I'm growing by 7 each time. Right? And I'm starting with 7. So that number is 7 plus 7 times 10. That's part of what I've got to do here. And maybe I'm getting ahead of myself. Maybe we should worry about that later. So what I need to do here is I need to think about how this is f of n equals 7 plus 7 times n minus 1. That's the thing I need to think about. And I need to take this and I need to translate that to sigma or summation notation. So I draw my giant sigma. I'm choosing to start at I equals 7. Or sorry, I equals 1. It is 7. And I want to make this go up to, we'll get to that part next. We want to make it go up to 77. So this needs to be 7 plus 7 times I minus 1. And I have to think about if this is my 10th term and this is an n minus 1, I'm going to highlight that instead of erase it. If this is my 10th term, but my 10 has to be my I minus 1, then I have to go up to 11 because 11 minus 1 would give me 10 here, right? And that's my last term. I think this is a really interesting problem. If I wanted to start with 0, it's almost trickier. Then I need to make this go up to my 10th term instead. And then I would have 7 plus 7i. So those would also match. All right, on the next one. So this one's going to infinity. All right, good to know. That's going to be easier. It's starting at 2. I'm going to think of it as a sequence again. We're adding 3 each time, so it's arithmetic. I know it's got to go to infinity. I've got to decide, am I going to start with 1 or 0? So if I start with I equals 1, then I'm starting with 2 plus, I'm adding 3 every single time, and I'm adding it I minus 1 times. Or if I started with I equals 0, I would still be ending at an infinity, but I would be adding 2 plus 3i over and over and over again. All right, next one starts with 1 over 1, ends with 1 over 20. So let's think how our first term is 1 over 1, second term is 1 over 2, 1 over 3, 1 over 4. So it's really like a 1 over n thing. Whatever my step number is, whatever my term number is, that's the number in my denominator. So this one I definitely want to start it at 1. It's going to be easier to write. So I'm starting at 1, and I'm going up to 20, and I'm adding 1 over n over and over and over again. Oh, except it's not n, it needs to be I. Gotta make sure that those letters match there. So for our last one, for our last two, this is one that I think maybe you should be trying on your own. My first one, I want to go from 1 to 5. Sometimes the lower and upper limit kind of print off on the side. It's just the font. There's nothing we can really do about it. So what this is saying is I'm doing 8i over and over and over again. 8i plus 8i plus 8i. But I'm plugging in numbers. I'm starting with 1 and I'm ending with 5. And they're going in order. So 8 times 1 plus 8 times 2 plus 8 times 3 plus 8 times 4 plus 8 times 5. So I can certainly go through and say 8, 16, 24, 32, 40. I can add them that way. But kind of a cool trick that I could do is I could say, well, all of these have 8. I'm going to factor out an 8 and make it 8 times 1 plus 2 plus 3 plus 4 plus 5. And that's going to make, let's see, 6, 13, 8 times 15, which is 120. So I really like this. I think it's a pretty cool thing that we can do. Okay, last one, I am adding 2 minus 3k over and over and over again, starting with 3, ending with 5. So 2 minus 3 times 3 plus 2 minus 3 times 4 plus 2 minus 3 times 5, adding them over and over and over again. So 2 minus 9 is a negative 7 plus 2 minus 12 is a negative 10 plus, let's see, 2 minus 15 is a negative 13. So let's see, the 7 and the 13 make a 20, and 10 is 30. We have negative 30. So I really hope that you see the connection with writing an nth term rule and writing something in this sigma notation. We really want you to see how these two are similar. Right? That's what our goal is today. And it's just kind of a cool notation to show adding things over and over and over again. It ends up being a really useful way to shorthand stuff. All right, as always, if you need help, please make sure you ask.